Hello, everybody.
Hello.
Thank you.
Sure.
We have a midterm on Friday. And before that, I should say quiz 0310 will be posted on Friday. So that is no distraction, just a tiny distraction to avoid that. Midterm 2 is on Friday. A few things about midterm 2, I can write here, I suppose. It will be, let me say 5 questions, 5 problems plus 4 conceptual, but I might make this 4. I'm still debating. So this is 4 or 5 problems plus 4 conceptual questions. That's the plan submission process. So that's one point. Second, I understand that time might be a problem, so be prepared. Be prepared for a short time. Right? So it also means that you have to, so I should say that D2L submission, it says it stops at 12:50, but I give a little leverage. There is a little leverage I give. I don't want to tell how much it is, but that is just so that the moment I give a new limit, then you go all the way till there, right? So expectation is that you should be all done by 12:50. If by any chance you cross this line, submit by email, but submit by email if necessary, but the acceptance depends on prior, I'll take fairness into account. So if you submit by email, then it is my decision that whether I accept it or not, and that will depend on whether I feel there was an issue of fairness with respect to other students. So that's one thing. But do send it to me. Like, don't assume that if I cross the 12:50 limit, I should not be submitting it. So do send it so that we avoid the technical issue. What else? Oh yes, no cover sheet will be posted. No cover sheet. Last time the cover sheet was posted primarily so that you have a feel for where the exam will be available and what it will look like. The purpose was not so that you sign on that sheet and scan it. So, but you have to write the pledge on the sheet of paper. And finally, be present on Zoom. Be present on Zoom with video. This is optional. With video. By optional, I mean being present on Zoom is optional. If you're not present with video, there is no purpose of you being there. But if you think that is not possible, that's perfectly fine. Again, if I see any inconsistencies in your exam relative to the first exam, or I have any reason to doubt, then the idea of the video is that this avoids that or at least give some proof that this was what was happening. So again, be responsible, and let's try to be fair to everyone. So okay, so that's all I have for the midterm. And of course, about the preparation, I had told that midterm 2 homework problems. Since I expect you guys to have gone through or you worked out the homework problems, that gets priority. Lecture examples, they're very close to, very similar to the homework problems, lecture examples. And finally, textbook solved examples. If you have limited time, go in that order. First, try homework, second, lecture examples, and third is textbook examples. And for conceptual questions, go for quizzes and textbook conceptual problems. But it's at this point, it is too late to probably go over all of this. But yeah, if time permits, that's where you should have. The expectation is that you should have done this more in a spread out manner. So yeah, that's my recommendation for the exam. Hopefully this helps. And going to the quiz problem, the question was, does when you're if you're on a slope, this is called on a banked road. So think of it. So we are going to talk about it today also. So think of this to be a banked road. So this is that's like a cone situation, and since this is a cone, your car will be inclined here, right? So if I were to show this as a cross section, you have a incline and a car using the notation that we showed last time. This is going into the page, so we see only 2 passengers instead of the top view will give you a view of 4 passengers. So the question is, what is the tendency for it to move? Usually we expect that the tendency of this car is to move outward, so the friction is inward. So the force of friction alone, mg, and normal force is inward. But that is if you're going very fast. That's also possible that this is if v is greater than a critical velocity. If you're going relatively slow, this is mg, normal force. And if you're going relatively slow, then the tendency is for you to fall down, right? You might have noticed this sometimes if you have ever watched any car races. Sometimes the cleaning, sometimes the tracks has to be cleaned and they are not able to go very fast. And at that time, there's a tendency for this to slip down. And when they tend to move downwards, the friction is upward. So yes, it is possible for the cars to tend to move inward also. So let's go through in detail this. This is broadly called banking of roads, a very good application of the circular motion and the force of friction that we have studied. Very elegant application if you want. So let's what is this on the chat? Get an email saying that they have to be on Zoom for the test. Any? What is it? Oh, yeah. So this was about the comment earlier that very specific students I have asked specially for them to be on Zoom, but that's a very small number. But in general, what I'm recommending is that please be on Zoom. That might help doubts a little. That's all. So Okay, so this is broadly called banking of roads. You might have noticed that often on interstates, when the interstate is taking a turn, the road is actually inclined towards, like if the road is turning this way, the incline will be towards the center of the circle that is formed because of the turn. By center of the circle, I mean this way. So that is a incline that is supposed to help with your motion. So let's see how that works. So let's uh, think about three problems, three situations. So let's say we are going in a circle, so circular motion with friction, or let's say without friction, right? Without friction, without banking. So that's so there are two things. It is without friction and without banking. That's the two parameters we are talking about. And second is circular motion. If you allow me to just, so this is with friction and without banking. That's the second scenario we want to talk about. The same thing here. This means that I'm copying this down again here. That's the same here, and that's the same here. Right? So this is with, so next let me talk about without friction. Let me just write it, no confusion. Without friction but with banking. So this is banking. And finally, I want to talk about with friction. This is everything included. And this is the closest you will get to real life, right? With friction and with banking. Actually, without banking is also relatively common. So that's a fourth scenario. So that's just four situations we want to talk about. Circular motion, circular motion. Okay. Case one is the simplest. Case one is the simplest because if you're having circular motion, you need some force to provide. So we are saying that there is a circular motion happening, and this is the car is somewhere here. 4 passengers. This is the top view, right? MG goes down, so the cross-sectional view would be this way. So that's your cross-sectional view. 2 passengers, so that is mg acting downwards, normal force acting upwards. And we have already said that if there is a circular motion, something has to provide the force for it to go in the circular motion. That means there has to be a radial force, and the radial force, one possible candidate is friction, but we said there is no friction. So without friction, unless you attach a rope or something to the center of the circle, it is not possible to turn. So you cannot, so if you're driving a car, you cannot turn on a frictionless And so notice that there is no banking, frictionless, unbanked road. And that's what happens on an IC road. If there is a turn, which typically is not banked, and IC means it practically becomes frictionless, and you cannot take this turn. The moment you try to take this turn, you tend to go in a straight line. So that is what we think of it as skidding or going off the lane. So that's case 1 is the easiest, right? Let's do case 2 next. So it's also.
Would an unbanked road also be the same as saying perfectly flat?
Yes, unbanked means perfect. I'll draw this a banked road. I'll be drawing this very quickly. So yes, unbanked is yeah. Let's use that word. Yeah, perfectly flat. Yeah, that's a good description. Yes, I'm just going to do that now. I'll draw the picture now. Okay, so now what we are saying is that, so this is a banked, and so case 2, right? So case 2, that is friction. No friction, sorry, frictionless. Frictionless. Did I say that? Circular motion with friction, not with friction. Without, oh, okay, so this is without no banking. Right? So yeah, not yet there. I'll come back to that, answering that question in the next case. Okay, with friction, no banking, again, we have a circular motion here. And our car is, the top view of the car is having 4 passengers. That means this is the top view. And this is the flat, this is ground, right? And the ground is making, so let's say theta equal to 0. So if this was inclined, that is what I mean by banked. We'll do that in a minute, but here, this is exactly flat. Like this is horizontal, ground is horizontal. And there are 2 passengers that we can see because the car is going into the board. Let's say the motion is in this direction. The forces acting would be mg acting downwards, normal force acting upwards, one puts off vectors, and now the tendency of this car would be to get thrown outward, so the friction is acting inward. So that's your friction, and that's your force of friction. This is moving in a circle, so there is a radial acceleration, which I show it here. This is showing the forces, but this is a different diagram altogether. But since this is empty here, I take that opportunity to show this is the acceleration. Acceleration is inward towards the center. It doesn't, like at this instant, it is horizontal, but somewhere else it is always in the radial direction and inward direction. And the magnitude of that is proportional to how fast you're going. Like it is v square over r. So let's write down our Newton's equation. So we have mass times acceleration is equal to mg plus the normal force plus the force of friction. That's the 3 forces, but split it immediately into the x and y direction. It's convenient. Here, remember our trick or a suggestion that I had made earlier, that choose your axis in the direction of the acceleration, one of your axes in the direction of acceleration. Acceleration is in the radial direction. In the instant we have shown, it is horizontal, so x and y will be in the x will be aligned with the horizontal. So if we say this is to the left, so this is minus mv square over r. Acceleration, remember, is v square over r. Magnitude of this acceleration. It's visible, yes. Magnitude of this acceleration is v square over r. Or angular velocity squared times r. This is the centripetal acceleration, and that's what goes in here. It's towards the left, and if I choose my x-axis to be toward positive towards the right, then that's the negative sign showing up. mg doesn't matter because it's in the vertical direction. Normal force is vertical direction. Force of friction is also in the inward direction. That's minus force of friction. That's here. A relation, I can immediately cancel out my negative signs. I'll do it right away in this step itself. I know you guys cannot erase this, so just write it down again once more. This is in the x direction. In the y direction, there is no acceleration. It is not flying off from the ground, so that's acceleration is 0. mg is minus mg, and the normal force is in the upward direction, and there is no force of friction. So we can read it out immediately there itself. So that's n is equal to mg. N is equal to mg. That's your two relations, but remember that we can talk about the extreme scenario where the force of friction is barely sufficient to take care of the tendency for it to fly outward, and that means force of friction has to be less than or equal to normal force, right? That's our condition. So that's the two relations, but we know that, oops, I should move my camera. So force of friction has to be less than or equal to mu s times n, but n is equal to mg, so that's mu s times mg. Force of friction, on the other hand, on the left-hand side is equal to mv squared over r. Right, that's the relation you get. If I want to analyze the extreme scenarios, what is it? How is the velocity related to the mass? So since I have this inequality in there, so I will write mv squared over r is less than or equal to mu s times mg. Notice the mass cancels out. That means whatever analysis we are making as to at what point, at what velocity will this start to slip, this actually does not depend on the mass. It doesn't matter whether it's a car or a huge truck that's taking the turn. And there is a limit here. If you go faster, so as far as you're within a certain velocity, you're good. So this is mu s times g times r, and this is square root of that. So if you know the force, your surfaces, like remember the coefficient of static friction is decided by the property of the contact materials. It is in this case, it will be the tire material with which the tires are made and the concrete that the road is built out of. G is a constant, and the radius. Often you will see signs when you're taking a ramp that the limit is 40 miles per hour or 30 miles per hour. That's pretty much decided by the radius, usually making a safe estimate of what your coefficient of friction could be on a general basis. Then the radius is what decides that, and the velocity is chosen by that. It is usually put on the safer limit. You can actually go slower, and that's perfectly fine. Like if your 40 miles per hour is the limit, then you can always go slower, and that's okay. In the next analysis that we are going to do, we are going to talk about banking, and in that, keeping that context in mind, let me define a parameter. So notice mu s is a property of the material. Right? This is the property of interface, if you want. Property of interface. We conveniently choose it to be mu s, but I can define it in terms of another parameter, And let me define that to be some angle. And you will see the motivation of this later on, the analysis. It will simplify the analysis a lot. So what I mean by this is that theta of S is simply tangent inverse of mu S. So this is a new property of the interface, which is defined as tangent inverse of mu S. A new number, but very convenient when we are going to compare it with what happens in banking. In principle, this is sufficient, but this is theoretically a new parameter. Okay, so that's your case 2. What we have learned is that if there is friction, but there is no banking, first of all, there is a maximum velocity with which you can take the turn. And secondly, notice what is providing. So if you have to go in a circle, remember there is centripetal acceleration. You cannot avoid it. If you're going in a circle, there has to be a radial acceleration. If there is a radial acceleration, according to Newton's law, there has to be a force. So we ask, who is providing the force? It's a friction, right? Friction is providing the force, and friction in this scenario is a wear and tear motion. This is not really helping the motion. Sometimes when you're moving in a straight line, often friction is actually helping you with the traction. Here, the friction is really causing wear and tear. If you were to slip even a little bit, that's a significant amount of wear and tear that will be caused on your tire. So that may not be the most best scenario if you don't, as we are going to see, we are going to bank the roads to avoid this. So we are going to find ways of not using the friction for providing the centripetal force. So the question is there a better way of going in a circle without using the friction, because friction causes wear and tear, but it should give us the same features. So that leads to the idea of case 3. Case 3. This time, let's take friction completely out. So there is no friction at all. Frictionless, and this is slightly counterintuitive, but give it a thought. But banking is, so there is banking. So there is no friction, but there is banking. And that leads us to the question of what do we mean by banking. So notice I first drew a circular motion, and that's still valid. That's your top view, and that's your 4 passengers. But in a 3-dimensional view, this will be a cone, right? So if you want, so that's your, so the roads, the car is going along the road like this. So that's a circular path we are taking. So this is a circle, is a cross section of a cone, if you want. Think of a speedway wherever there are cars racing, going in circles and participating in a race. Usually, this is very dramatic there, because they're going very fast. The incline could be very high. For example, some of this banking could be as high as 35 degrees or so, if I remember correctly. Now, how does this incline look like in a cross section? So in a cross section, this will look like, so that's your horizontal, right? But it makes an angle theta with respect to the ground. So that's this angle, if you want. So that should clarify what banking is. This is not so dramatic on the interstate. On the interstate, this might be about 10 degrees or something, because we don't go very fast in that. So it's usually about 10 degrees, I think. Okay, so here the car is showing only 2 passengers, again going into the boat. So this is the motion in there. And now let's ask, what are the forces acting on this? That is mg acting downwards. That's the same as earlier. And there is normal force acting this time perpendicular to the surface, but now that also means that it's making an angle, right, with respect to the vertical, and that's angle theta. Same angle theta will go in there. Okay, so that's, oh, what are the other forces? In the earlier case, there was a force of friction also, but we don't have that because we're talking about frictionless, right? So there is no force of friction in here, but we still want an acceleration, right? That is an acceleration inward. That's your acceleration. That's the same, right? If we are going with velocity v, the acceleration stays. But there are only two forces, and now you notice that since this is making an angle, oh, there is actually acceleration is in this direction. It's horizontal towards the center of the circle. Center of the circle is in this horizontal line. So if I were to draw this acceleration, it is in this diagram here. That's your acceleration. Usually acceleration is not confused with the forces, so you want to draw that separately, slightly away. But that's just a advice. Okay, so that's your two forces, and then you ask, oh, what provides that acceleration? Now you notice that the normal force has a component. So what provides the centripetal acceleration? Which force is providing the centripetal acceleration? It is the normal force that provides a component of the normal force that provides, and that's the application here. We are avoiding friction, and even though there is no friction, apparently you can actually take a turn. You would think that if this was frictionless, there's no way you can take a turn here, you're going to slip down. No, you will not slip down because the dynamical, for dynamical reasons, you will have to go fast enough so that the normal force can provide that acceleration. This is the closest you can think of how Earth is going around the sun. Often, if you think carefully, or if you critically think, you will wonder that, oh, how is it going? Why is it not actually falling towards the sun? But it's actually going in a circle just so that it can provide the acceleration that is needed to balance it. So what's our equations now? A slight difference, right? MA is equal to only two forces now, mg plus the normal force. We still choose, notice this is slightly different from what we have done earlier. Earlier, we used to, whenever there is an incline, we will change our axis, right? We would choose our axis, one of the axes to be aligned with the incline. This time, we don't want to do that because, again, our guideline was that choose the axis, one of the axes to be parallel to the acceleration. So we will choose this to be our axis. So that's your x, and that's your y. And this time, since normal force is not in the y direction, so I had to take components along that. So if I were to write these equations down, so mass times acceleration, that's v squared over r, and that's minus if you want, and that's equal to mg has no component in the x direction. Let me write this as the x component. That's the x direction, and the mg has no component in the x direction, but normal force has, and it is equal to n sine theta. And this is minus, right? But again, like last time, I will cancel away the minus right here and get that as our equation. In the y direction, similarly, there is no acceleration. Notice again, we are talking about there is no motion, and this means that mg has to be exactly equal to the component of the normal force. When I say there is no motion in the y direction, that means this is not sliding away outside or inside. So this is maintaining the radius of the circle, if you want. So that gives us, let me write this to be mg is equal to n cosine theta. Notice when we had chosen our axis to be aligned with the incline, then we would have got mg cosine theta as the normal force. So this is a different coordinate system. So be aware that we are doing slightly different from what we had done earlier. That's okay. That's good. So if we are interested in the velocity again, like is it possible to move on this frictionless inclined surface? So again, imagine that there is a cone and it is frictionless, and you want to drive on it, and you might wonder whether it is possible to drive at all, or drive in a stable manner so that you don't slip away. And apparently, yes, so there are equations which seems to suggest that it is possible. So let's actually find out what's the velocity we have to go, right? So let's divide this equation because we don't know much about the normal force. So let's get rid of that normal force. So let me divide these two equations. I'm dividing these two equations. Notice M cancels out, normal force cancels out. So M canceling out means that whatever analysis happening here is independent of whether it's a car or a truck. So I get V squared over R times G has to be equal. Normal force cancels, sine theta over cosine theta is tangent theta. And we learn that velocity with which it has to go is G times R times tangent theta. And notice the right-hand side, unlike the earlier case, that was less than or equal to, very easy to take a turn. When you're taking a turn, you don't try to be exactly at a certain speed. If you're going slow, that's okay. You're not going to slide off. But here, right-hand side is exact, like R is fixed because the turn of the curve decides that. G is a constant. Tangent theta is the banking. You don't have much control on that. The road is already built for you. It is already banked for you. That's a fixed velocity. If you happen to be going slower than this, you will slide into so the radius will adjust itself. What can be adjusted radius as far as the system goes, it will tend to skid towards the center if you're going slower, and if you're going faster, you will go R will increase. So velocity is proportional to the radius. The only thing possible is to change the radius, so you will either skid outward or inward. I would like to compare this with the earlier situation. Notice just on the left-hand side, we had velocity less than this. This is very different because this is less than or equal to. Velocity has to be less than or equal to. And again, since we introduced this mu s is equal to tangent theta s, there is a lot of similarity between the two. But this is much easier, notice, because velocity, if you're a driver, you don't have to be very skilled. You just have to make sure that you're less than this speed, whatever is decided by the coefficient of friction. Here, you have to be extremely skillful to be able to take this turn without skidding or slipping towards the inside. That's not convenient. So I said that, oh, banking is going to be a nice feature, but here it seems like you can take a turn, but you have to be extremely skillful. But that's when I did not introduce the friction at all. So now let's come to real, reasonably real, like as much realistic we can get. Let's introduce friction and banking together, and that's case 4. And as one can expect, mathematically, this will be a little more challenging, but we can handle it. So it's case 4. This is having friction plus banking. Remember, banking is given in terms of angle theta, and friction is given in terms of angle theta s. And you will notice that this will be very, those angles is what is going to decide everything. Let's put our diagram again. So that's your car going in a circle. It's very clear what's happening. That's your acceleration towards the center. If it has to go in a circle, it has to be having a centripetal acceleration. That means that has to be a force providing that acceleration. And this time, the only difference is that we have a new force, that is a friction. That's mg, and that is a normal force. And next, we have to ask ourselves, what about friction? What direction does it exert itself? In the early part of the class, that was the quiz question. If you go very fast, the friction is inward because the tendency is going to throw outward. But if you go very slow, the friction can be in the opposite direction also. So let's assume that you're trying to go faster than a critical velocity, and that critical velocity will be the case 3 that we talked about, right? If there was no friction, that is a velocity, very special velocity we have to go, that will be act like your critical velocity. And if you're going faster than that, so there is a case now we are saying that velocity is greater, so you're moving with a velocity faster than gr tangent theta. And if it was frictionless, you would just skid outward, right? But now friction is able to oppose that. So apparently you can go a little more faster than that. So that's your diagram, and maybe that's your angles, if that's all clear. The angle, so let me make this diagram again. That's mg, that's your normal force, and that's your force of friction. That's angle theta, that's angle theta, because if this is angle theta, that's your 3 forces that are acting, and acceleration is horizontal, right? Again, we choose xy to be in the horizontal and vertical direction, and our Newton's law now has one extra force, equal to, that's mg plus the normal force plus the force of friction. Analysis is very simple or very analogous, not simple, but we have to introduce the force of friction also in there. So let's again do x direction. It's again like earlier, there is mv square over r towards the left. Reading it out, it gets a contribution from the normal force like earlier. Right, like earlier, so that's n, what's the contribution? It was n sine theta earlier, right? So that's n sine theta. But now friction also can contribute to the centrifugal towards the inward radial force. So earlier, remember when there was no banking, friction was providing. So here, these two are providing, but at a certain angle. So what is the friction? So it's plus force of friction, and that's cosine theta. And what about in the y direction? These two, all these forces has to be canceling if we don't expect it to slide. That means move outward or inward. That means mg, if I were to write mg on one side, normal force is going to balance that, so it's positive, so it's n cosine theta. And the force of friction has to be subtracted. You don't need as much normal force as was earlier needed. So there is a force of friction acting in the downward direction. So that's minus the force of friction, this time in the sine theta, right? Because angle is with respect to the horizontal, so y direction gets sine of the angle. That's your difference from your earlier situation. Notice if you set force of friction equal to 0, you get exactly the same relation that we had earlier. Now, at this point, let me talk about the, in general, the force of friction has to be less than or equal to mu s n, remember. So force of friction has to be less than or equal to mu s n. But let's talk about the threshold. What's the maximum velocity you can go? This is a, we said will be a critical velocity, but how fast, how far can we go away from this velocity? Is there a maximum limit or not? And that's decided by the force of friction. So I'll replace this force of friction with mu Sn. And this was, so that's force of friction. But the moment I have replaced it, I have changed my analysis completely. This is no more any velocity. This is the max velocity. So I should change this to V max. So let me change this also to V max. This is V max now. At the maximum velocity I can go without sliding outward. So I replaced force of friction here with mu Sn and velocity with V max. And now I do the same trick. I divide these two equations out. When I divide these two equations out, the masses cancel here and the normal force on the right hand side cancels out. And what we get is V max square divided by G times R is equal to sine theta plus mu s cosine theta divided by cosine theta minus mu s times sine theta. This is, I'm going to use the trick that I said earlier. I want to replace this mu s with tangent theta s just for having a feel for what is happening. Is there a simplicity in this analysis? So it seems like this is an equation not very friendly to read, right? So, but that is a nice interpretation here. If we were to replace mu s with tangent theta s, and let's also do one more thing, divide each term in this with cosine theta. The first term becomes tangent sine theta by cosine theta. That makes it a tangent theta. Second term, since I divide by cosine theta, that's not there, but mu s is tangent theta s. That's the second one. Third one, I divided out each term by cosine theta. So that's 1. And that's minus of tangent theta, because sine theta divided by cosine theta is tangent theta. And mu s is tangent theta s. And if you're very comfortable with the trigonometric relations you have seen, if you have studied, you will immediately identify that's the double angle formula for tangent, right? So you would immediately see that, oh, that's, and that was the idea of replacing that theta with tangent theta s, or mu s with tangent theta s. So this is tangent of theta plus theta s. So what's our maximum velocity? There's a nice interpretation now. The formula has not changed significantly, just that there is an angle. So this is like saying the friction acts like a banking angle. So you can go a little faster. Remember, tangent function is monotonic. So if you increase the angle, your tangent function has increased significantly. Actually it goes it doesn't go linearly, it increases very dramatically. And in that sense, velocity is much, you can go significantly larger. And this is, so you should say velocity itself has to be less than or equal. Now, while we were doing this analysis in the very early, if I go up a little, I had pointed out that it's also possible that you might be going very slow. If you're going very slow, the friction is towards the outward direction. And what would change is that all these quantities will become in the first quadrant instead of the second quadrant, wherever it comes in. And interestingly, the analysis leads to, so this is a velocity that is less than tangent theta plus theta s. So velocity has to be greater than or also equal to. This is an analysis. I'm just writing it down. This is theta minus theta s. Right. So if you're going slower than a certain angle, a certain velocity, the friction is in the upward direction, but there is a limit beyond which you will start slipping in the inward direction. And if you're going fast enough, there is a maximum velocity with which you can go, beyond which you will start moving in the outward direction. In general, our interest rates are designed in a safe manner where this is pretty much applicable for most of the times. But remember, friction changes when it rains. So whenever you're taking an exit in a ramp, or whenever there is a guideline on a velocity for the ramp, you should be very careful. Those guidelines are for dry situations. In wet situations, your angle theta changes significantly, and or if it was an icy road, those angles could be significantly off, and then we are always advised to be careful, and that's that feature showing up in there. So this covers the banking of roads, and I will stop at this stage, and I'll wish you luck or good wishes for the exam. So I don't plan to make it too hard, but time might be a problem. I can foresee that, but I'll try to make it 4 questions for plus 4 conceptual questions. Thank you, and see you on.
How on earth did you go from sine plus Ju s cosine theta over cosine theta minus Ju sine theta? How did you get from that to the thing with all the tangents?
Okay.
Like,
so
where does theta s come from?
Oh, that was, remember, mu s was tangent theta s. Okay, let me do that slowly. Okay. So I'm going to write the same equation, but divide each term by cosine theta. That's perfectly okay, right? Mu s cosine theta divided by cosine theta. That's your first equation. Am I visible? Yes. And that's cosine theta divided by cosine theta minus mu s times sine theta over cosine theta. That's a mathematically valid operation. Agreed?
Okay.
Right? So that's tangent theta now. Right? Now at this stage, first of all, I replace mu s with tangent theta s. Okay? So if you allow me to do this in the same line here, that's tangent theta s. And that's tangent theta s. With me till now?
Okay.
And then I just replace this. This is equal to tangent theta. In the board space, yes. And this is plus tangent theta s divided by, this is 1 minus tangent theta s times tangent theta. I wrote this in this tangent theta times theta s, but that's the same thing, right? That's, yeah, good question. Yeah, I sort of jumped steps, I suppose, but thanks for asking. Hopefully clarified.
Yeah.
And
how would we apply theta s in a problem? Like, how would we get that?
Just as I said, tangent theta s is equal to mu s, correct?
Yeah.
So let us say that mu s is given to you, right? So that's, let's say mu s is equal to 0.5, correct? So theta s would be tangent inverse of 0.5.
Okay.
Whatever that value comes out to be. Okay, so for example, if I were to do this tan inverse of that's about 27 degrees. Is that clear? Maybe I should have done that right when I was introducing it, but I had to maintain a speed so that I can cover it. That's the challenge always. But yeah, good question. And these questions help me elaborate on this.
All right, thank you.
Thank you. Mhm. Any more questions? If not, I'll stop.